Hello students, this is a lesson on triangle similarity. And hello, nice to see you. So to start this concept, we want to think of a dilation. So I'm going to jump over here, and there are 4 types of transformations. There's reflections, translations, and rotations that we talked about, and those keep the shape the same. Today, we're going to talk about making the shape bigger or smaller. Okay, those are dilations. And play with this for a second. So we have a triangle. You can see it. And it's triangle JKL. And we want to make that bigger. We want to dilate it by a scale factor of 3, which means we want it to get 3 times as big. So I'm going to use these tools. This is a Desmos activity. It says, for a dilation, you need to choose a point, or we call that the center of dilation. And they're telling us that we're going to dilate from point R. And the scale factor that we're going to dilate it is 3. So we're going to dilate this with a scale factor of 3. It says to select some object to apply this transformation. So I'm going to choose line segment JL, and I'm going to apply that dilation. Whoa, it just got how much longer? 3 times as long. Okay, I'm going to do the same thing. I'm going to dilate line segment JK from point R by a scale factor of 3. And then to finish this triangle, I will dilate line segment KL. Its image will be out here, 3 times as big. And that's what it will look like. 3 times as big. If on your phone you go like this on a photo and you make whoop bigger and you smaller. This is what the math is being programmed to do inside your phone. It has a scale factor somewhere, and it's telling when you move your fingers this much, it makes the picture that much bigger and that much smaller. Let's check our answer. And you can see here, it's really interesting that each point, so we did line segment JL first, and it was this long. And it looks like point J was 2 units away from R. And after we dilated it, it was now 2, 4, 6 units away from R. So the center of dilation is pretty interesting. So if this is 1 unit, then I had to triple it to get out to L prime. Okay, same thing here. If this was 1 away, this was 1 away, this is the K prime would be 3 away. So it's not only that the sides are 3 times as long, it's also that the distance from R is 3 times as far. Okay, let's go back to this. So that's what we did. We dilated triangle JKL by a scale factor of 3. All right, in medicine, dilation means a couple different things. One thing it means is that your pupils will dilate. So if you shine light right in your eye, your eyeball is gonna reduce the amount of pupil or increase the amount of pupil. It's also when women are about to give birth, there's something called dilation. But in geometry class, this is what dilation means. It means that you are, let's see. So first of all, we use a capital D for dilation, and then it has 2 things here. So the first number is the scale factor. So how much bigger or how much smaller are you going to make it? And the second number is the point or the center of dilation. So here's the center, and then how much bigger are we going to make this line segment? This part's not as important. You can either make things bigger or you can make things smaller. So if we're making something bigger, we're calling it an enlargement, and that means your scale factor is like 1, 1.2, 1.5, 1.7, 2, 5, 16, 24. That's your scale, that's how much bigger it's getting. If you want to make something smaller, we call that a reduction. And for that, if I want to make something smaller, it's going to be a fraction between 0 and 1. You're not going to ever have a negative scale factor. That doesn't make sense. If you're on a coordinate plane and you just have a dilation with a scale factor of n, that means the center is assumed to be 0, 0. Let's apply it. What's the scale factor of here? And how would you use the scale factor with the transformation notation? So first of all, what do you guys think? Which one's the original and which one's the image? That's important for a dilation. So we can look at the relationship between the two triangles. How much smaller is this one? Or how much bigger is this one? It kind of depends. So one way to look at this is that from A to B is 2 units. And from A prime to B prime is only 1 unit. So what does that mean? Do they look like the same size? Good. Okay. Yeah, so this one is 2 times bigger than this one. So the way we would write this is if you take triangle ABC, you would need to dilate it by how much from point P? Let's see, is it getting smaller or bigger when it turns into A prime, B prime, C prime? It's getting smaller. So if you put a 2 right here, you would get it wrong. Okay, the scale factor for this one, this is a reduction. So the scale factor is 1/2. This is half the size of this one. So the way we would write this is like this, capital D for dilation, and looks something like that. And then maybe I would say that is going to equal A prime, B prime, C prime. And one thing to notice is they're both right triangles. So what shapes can be similar? Some right triangles are similar to other right triangles. Okay, another thing that's interesting about this is if I draw some rays coming off of point P. There's a ray right there. If you look at from P to C is basically 3 over and 2 up, right? To get to C prime, from C prime to C is also 3 over and 2 up. So this distance and this distance are the same. C prime is halfway between point P and C. You can look at that here too. Okay, I can look from P to A is 1, 2, 3, 4, 5, 6. From P to A is 6, but from P to A prime is only 3. So there's a lot of ways to think about this. So the whole thing was 6, and that's 3. It turns out that in similar triangles, so we could write triangle ABC is similar to triangle A prime, B prime, C prime. It's a reduction by scale factor of 1/2. And it is, all the angles are the same. These are both right angles. These are both right triangles. So one thing that's true about similar figures is that their angles are congruent. So angle A is congruent to angle A prime, angle B is congruent to angle B prime, and angle C is congruent to angle C prime, but the sides are not the same, okay? So what's the relationship between the sides? AB is 2, and A prime, B prime is 1. Okay. How long is AC? AC is 1, 2, 3, 4. And A prime, C prime is 2. So these ratios are equivalent, right? Well, we call that, and then if I was going to do this, this is 2 and this is 4. So this is 1 squared plus 2 squared is square root of 5. Okay, and this is 2 squared and 4 squared, so that's 16, 20. So this is the square root of 20. Square root of 20 happens to be 2 times the square root of 5. Okay, so this is also twice as long. If you have from B to C is 2 square roots of 5, and from B prime to C prime is only 1 square root of 5. Guess what? That just equals 2. Square root of 5 divided by square root of 5 is 1, so it can go away. All right, so we call this the sides are in proportion. They all have the same fraction that they simplify to. So I kind of skipped this. This symbol right here means similar. So shapes that are similar, all squares are similar. Are all triangles similar? No. Are all rectangles similar? No. So squares are all similar because what are all their angles? Their angles are all 90 degrees, okay? And their sides are all the same also, which means that, like, if this side is 1 and this side is 3, this is 1 to 3, this is 1 to 3, this is 1 to 3. And so the proportion of the sides is going to be the same. Now, similar means same shape, essentially. Like that you can build a shape that's the same, exactly the same kind of proportion. So some rectangles are super long and skinny, and some rectangles are short and fat. Can I squeeze this one and make it bigger and smaller and ever make it look like this? Just by enlarging it or reducing it? No, I can't. So these two rectangles are not similar. What about circles? Are circles all similar? No. Yes, all circles are similar. What about isosceles triangles? Are they all similar? These would not be similar. Excuse me. Okay, what kind of triangles are similar? Are all right triangles similar? No. Some are isosceles, some are scalene. All right, how about these two triangles? Are these similar? Is there a composition of transformations that could get that one to exactly match up on the other one? Yeah, now this one's bigger, right? So there's going to be a dilation involved here. Do these triangles look the same? Just one smaller than the other? They do to me. They're both obtuse and they're both scalene. They're both obtuse scalene triangles, so they're probably similar. How can we get this one to match up on this one? Okay, I'm going to rotate. That's what somebody said in class. So I'm going to take point. I'm going to use yellow for my rotation. I'm going to draw a line from the origin through X, and I'm going to go through the other side like that. And if I'm going to take point X and rotate it 90 degrees, 180 degrees, where is it going to land? Okay, it's going to land right here. This is going to be X prime. And remember, we're trying to get X to match up onto J, and it's getting closer. Okay, so if I rotate this whole triangle 180 degrees, where is it going to land? I'm going to do the same thing with Z. So I'm going to do another ray out to there. And I'm going to extend it so it's a straight line out to there. And